Hello students. So far we have read about capacitors, capacitance, combination. In this combination we have seen a series combination as well as the parallel combination, and we have read about the series combination in detail and derived the formula for series combination too. Now it's high time for us to understand the parallel combination of capacitors and to derive a formula which will help us to find a capacitance for given parallel combination. Okay, so in today's class our topic is parallel combination of capacitors. Parallel combination of capacitors. Okay, so parallelly how are we connecting capacitors? See, this is capacitor number 1, then this is capacitor number 2, this is capacitor number 3. These all capacitors are having the same node, same junction. The current flowing from here, here and here is coming and passing through the same junction, though the charge over here and over here is different. Okay, the charge coming from here is I. According to Kirchhoff's law, this get distributed in I1, I2 and I3. Okay, and this moves and again reconciles at this particular point and then moves back to the given circuit. Okay, this is the battery which provides the potential V. Now while we were reading about the series combination, we have seen that capacitance is given as Q upon V. Here this is the thing which we need to find, for which we are struggling and for which we are deriving few things. So the two components which left are here charge and voltage. We have seen the charge is constant in the series combination. So when we talk about the parallel combination, our charge is variable. Our charge is variable. And when we see about the potential across the capacitor C1, C2 and C3 or up to any number Cn is constant or is same. So here, as this current, what is current? Current is charge per unit time, I equals to Qt. So if current is changing, it is very much clear that our charge will also change. So when this current is passing as I1, I2 and I3 from capacitor C1, C2 and C3, then there is a charge here which is Q1 over here, Q2 over here and Q3 over here. Okay, but the voltage which is passing from here is coming as such and passing through all this system in the form of the same voltage, that is V. Voltage or the potential difference, anything, is same across the all capacitors C1, C2, C3, any of it. Okay, so this is the basic over here, and then now we will start our journey of understanding parallel combination and deriving the given formula for the parallel combination. Here again the basic formula is C equals to QV, and because Q is changing, we will write Q as changing, that's why we will write Q formula as CV. Charge is given by the product of capacitance and voltage. Charge is given by product of capacitance and voltage. Okay, now we will start capacitors in the parallel combination. See over here, this is the figure 1 and this is the figure 2. Here see, C1 and C2 are in parallel combination and voltage is provided across here. So this is having a charge Q1 and this is having a charge Q2. Now in this combination we have C1, C2 dash 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 up to Cn. This one is having charge Q1, this one is having charge Q2 and this one is having a charge of Qn, but the potential across all is V, the same potential. Okay, this is clear, I hope so. Now the figure shows two capacitors arranged in parallel. In each case same potential is applied across the both capacitor. This is very much important. In series combination Q is same, in parallel combination potential is same. So you have to actually relate it like SQPV. See, when we write ABCD here like ABCD, I'll just change the pen, E F G H I J K L M N O P Q R S T U V W X Y Z. Okay, all I'll write here. See, this is our P and this is our V. They are far away, right? And this is our S, this is our Q. They are nearer, right? So remember it like this, S and Q are nearer, so they are same for each other. So in series charge is same. Parallel and potential are far away. They are like protecting brothers. They are outside Q and S ka system. So they are like protective brothers. So they will stay together. P and V are like protective brothers. So they will stay together. So in case of parallel, voltage is same. This is for same. Okay, remember it in this way. But plate charge on capacitor 1 is plus Q1 and on capacitor 2 is plus or minus Q2, which are not same. So Q1 is given as C1V and Q2 is given as C2V. The equivalent capacitor is 1 with the charge Q equals to Q1 plus Q2. For series combination, if you remember, we have used V combination equals to V1 plus V2. But for here parallel combination, as charge is different, the formula we are using is Q combination equals to Q1 plus Q2. Okay, now as I have told you, C equals to Q upon V and hence Q equals to CV. This formula we will substitute for Q1. Q1 will be C1V and Q2 will be C2V. V will remain same as we are reading it already. The potential difference V, for potential difference V, Q equals to CV. This is the combination charge, combined charge, not like this is combination charge, but we will write it as combined charge. Q equals to CV, that is combined, and this one is for Q1 and this one is for Q2, C1V plus C2V. See here, from here this is picked up and wrote over here. Now the effective capacitance from this equation number 3 comes to be combination, effective combination C equals to C1 plus C2, C1 plus C2. The general formula for effective capacitance C for parallel combination of n number of capacitors. Now here we are defining n number of capacitor. So Q equals to Q1, Q2 plus Qn, and for Q it is CV, for Q1 it is C1, V, Q2 C2 V2, for Q3 it is C3V, for Qn it is CnV. So we are adding up all. Here the common comes to be C dot V equals to V dot C1 plus C2 plus C3 up to Cn. Okay. So this V and this V will cancel out. So the C, the effective capacitance will come to be C1 plus C2 plus C3 up to Cn. So this is the effective capacitance when capacitors are connected in parallel combination. Effective capacitance when capacitors, or write it as when n capacitors are in parallel combination. Now we will just go for a short summary of what we have read in this section, and then we will end up our class. Okay. Now first of all we will go for two capacitors, and here we will go for n capacitor in a similar way we did for the series combination. Now in this case they are in parallel combination. Kindly make notes along with this so that you will understand it for better. So this is C1, this is C2, and here for n number this is these are the n capacitors like C1, C2 and Cn here. The basic formula for both the things will be capacitance equals to Q upon V. Here capacitance C is what we are trying to find, and Q is variable across parallel capacitors, and voltage, the potential difference provided will remain same always in this combination. Okay, in this combination. So this is what we have got. As we are dealing with a variable charge, we will define the charge as CV from equation 1, from this equation. This is equation number 1 and this is equation number 2. Now in this combination we have Q combined equals to Q1 plus Q2, two charges. In this case we have Q combined equals to Q1 plus Q2 dash 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 Qn. And from equation number 2 we know that Q1 equals to C1V, Q2 equals to C2V. Similarly here also from equation number 2 Q1 equals to C1V, Q2 equals to C2V dash 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 Qn equals to Cnv. Now we will take these as equation number 4 and this as equation number 3, this as equation number 3 and this as equation number 4, substituting value from 4 into 3. From equation 4 into 3. Similar here from equation 4 into 3. What we will get is Q combination equals to C1V plus C2V. We know from here from equation 2 Q combination equals to V into C combination. V into C combination. So we will substitute over here. This we will take as 2i. From 2i we will substitute the value of QC, that is V into CC equals to C1V plus C2V. Similarly here from equation 2i we will get it like, first thing Q combination equals to Q1 V plus Q2 V plus dash 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 Qn plus V. and from equation 2i we will get VCC equals to Q1V plus Q2V plus dash 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 plus QNV. So here in both these the VV will get cancelled out as it is same across all the capacitors. Okay, and this is not Q1, kindly mind it, it is C1 CC. Okay, C over here, C over here and C over here. So kindly mind this one, and then it will be like V is CC equals to C1 plus C2. This is the combined result for parallel combination. Similarly here CC equals to C1 plus C2 dash 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 up to Cn. So this is the resultant capacitor for parallel combination. Resultant capacitance for parallelly arranged capacitors. Now we will solve one very little problem here. We are having capacitor C1 and C2, C3. Okay, capacitor C1 is 4 microfarad, C2 is 20 microfarad and C3 is 36 microfarad. Now these are arranged parallelly. We have to find the capacitance for the combination. How do we find? As these are arranged parallelly, capacitance for the combination will be C1 plus C2 plus C3, which is equals to 4 plus 12 plus 36 microfarad. 36 plus 4 is 40, 40 plus 12 is 52. It comes around 52 microfarad as answer. So this is as simple as this to find a series or a parallelly combined combination capacitance for the given capacitors. So that's all for today's class. We'll meet up in the next class with another new topic, and enjoy these topics. These are easiest as well as interesting and the most scoring topics in the chapter. Okay, so see you in the next class. Till the time, bye bye, have a good day.